So you're stuck. It's right before Christmas and you're stuck. But then you realize that there's a huge difference between guessing correctly before the DNS server does and guessing correctly in the time frame it would normally take the DNS server to respond. Because who tells us that the DNS query will actually reach the DNS server? If it doesn't know about the query, it will not respond. So what does Squid do then if there's just no response? It will wait for 2 minutes. And 2 minutes is enough time for us to just put all guesses in the queue and just guess them all. So all we have to do is kill this firewall. So, okay, you could say, you know, you placed that Ethernet adapter, and of course I did. I mean, this is my story. But there are lots of ways that you can make the UDP datagram drop. But I really want to present this other Ethernet bug as well, so we're going to be using that. Writing NIC drivers is hard. Why? Because you actually have to support all sorts of different hardware which have the same name, but they're slightly different, and then they have slightly different bugs, but you have just one driver. And you cannot get documentation for it even if you, I don't know, sell your soul to the devil or sign a non-disclosure agreement. And sometimes this whole business of writing drivers seems like an experimental science when you read the mailing lists. So this is what the driver maintainer says, and I love this quote, so I put it on the slide in full. He says that the RX mux size register does not work as expected, and incoming frames whose size exceeds the MTU actually end spanning multiple descriptors. So this is the same that we saw with E1000. If you have a frame that's longer than a buffer, it will just span multiple buffers. That's it. But what's different about this card is that the length field, which will be reported, is going to be the length field of the entire frame, and not just that of the one in the buffer. So you write past the end of the buffer you just allocated, and you get memory corruption, and it's all bad. Or there's some garbage in the size field, but we're going to come to that later. Okay, so he proposes a patch. He says, first of all, I would like to disable hardware filtering, because so far it only proved to be able to trigger some new fancy errors. Secondly, drop all multi-descriptor frames. Anything that is in more than one descriptor, he actually means buffer. Anything that's in more than one buffer, just drop it. We're not handling this. Okay, so this is the change. Instead of saying the maximum size that you may receive is RX buff size, which means enable hardware filtering, just tell it, you know, receive anything, disable hardware filtering. Well, in 2009, adapters seem to be different. What was actually found out is that RX mux size with these new adapters is not the size after which hardware filtering is enabled, but it's actually the size the adapter thinks it can copy into the buffer. So they made that check, so they patched it back. So wait, I'm going to go back a slide. That's not good style, I know, but look. Minus, plus, plus, minus. So now hardware filtering is enabled again. And remember François' words, so far it only proved to be able to trigger some new fancy errors. And that's something we're going to be using. So what we did was we did MTU scanning, meaning we just sent frames of all possible MTUs to the adapter, and we just see whether something weird would happen or not. And we found out that when you send a frame of exactly RX mux size bytes, then the adapter will show some really fancy errors, as François put it. It will actually report that it has received multiple multiple fragments of a frame, and each fragment is 8,000 bytes in length. So that can't be, due to the Ethernet spec. You can only have 9,000 bytes, so that's obviously some kind of bug. And then device and driver lose sync, because the device is just reporting garbage. And now the RX buffers contain old frame payload. When you send new packets, the RX buffers will actually contain old frame payload. But what's more important is the RX descriptors, the meter data, the length field, the status, all of this contains old frame payload.
Very nice.
So there are two paths in the receive function, and they are both completely controlled. Well, the path we take is completely controlled by the status register. And we completely control the status register, so we completely control the path that we're going to be going. And there's one path which is the reset path. And when you hit the reset path, everything goes back to normal. Everything's good. It's like nothing happened. When you hit the receive path, some junk will be handed upward instead of the packet which actually arrived. So now what you can do is, since we control the status register, we started writing proof of concept exploits which would basically just spray the RX buffers with some value so that that is then transferred in the status register. Then we would send the offending frame, meaning the frame with that length of RX mux size, and then send a ping to get an RX interrupt triggered so that this would actually be handed up. Now if you spray with A's, something nice happens. You get a complete frame of A's of size 317 handed upwards. Now 317 is 321 minus 4 for the checksum, and that is in hex 0x141, which is, well, they apply a mask, so it was originally 0x4141, which is AA. Okay, so that's our payload. When you spray with E's, you hit the reset path. And now when you spray with A's first, and then with E's, you actually get to drop N frames, some amount of frames you want to drop, and then the adapter goes back to normal. That was the elegant case of making sure that the DNS packet, the DNS query would never reach the DNS server. Here's a brutal case. I like this a lot more. The brutal case, you spray zeros, so then you get a packet size of -4. And then you need to pass that first check, and you do pass the check because these are both signed integers, so it's a signed check, and you'll just see, oh, packet size is -4, and RX copy break is, I don't know, 1000 or something like that, and you pass the first check. So then you go down to the allocation of the buffer, and you think, oh, I'm never going to pass this check. Net IP align is actually 2, so packet size plus 2 will be -2, and when we cast to unsigned, it will be, just huge number. We can never allocate this, so it will never pass this check down there. But we really wanted to pass that check. And we're lucky because it does padding for us. So it will add 32 more bytes. So then it says allocate 30 bytes, so we get to pass the check. And then we copy just huge amounts of data into, 4 gigabyte into your kernel memory. And it's a beautiful crash, and it's an interrupt context. And I wish there was a haiku about blinking keyboard LEDs. The attacker's view, we're done. So I actually have a point, and I have time to make it. Here's what I want to say. The security of a network component depends on its environment. You shouldn't, Squid is a really good example, because Squid basically places all of its security into the hands of